All right, good morning. 2024 September 18th. Uh this one's a new concept called prediction surface in ArcGIS. Uh because we have to encounter numerous continuous phenomena and the there's no discrete boundaries. So we have to implementing, interpolating, predicting on the values based on sample data. Based on sample data, so you can model dynamic environmental phenomena, analyze hotspots, and we will have three methods using EBK, kernel interpolation with battery method, using topo to raster 2. So we just made some interpolation service. And here's the basic concept of interpolation. Surface 3D, 2D. The certain uh, application scenario which includes contour 3D surface at given point. First law of geography is a primary assumption of spatial interpolation is points in the
Vicinity. Vicinity.
same vicinity are more similar to one another than they are to points that are far away. That's very important part. If you want to make spatial interpolation, must make sure the data is spatially dependent. So, for example, in a high-income city, in which a block we have both rich and poor household, interpolation will not work. That's why we probably have to put the battery into consideration. So what's spatially dependent also means autocorrelated. For example, elevation, precipitation, crime level, property value, but not a television per city block, cheeseburger consumed per household. So there are two different interpolation methods. One is called deterministic methods, another one called geostatistical methods. And the difference is a deterministic interpolation methods only run on mathematical formulas and rules to predict unknown value based on value of surrounding points. They do not count any spatial variability or randomness. They only use proximity-based rules to assign values to unknown locations. For example, IDW and spline IDW only assumes that the points closer to each other are more similar than those far away. The value at unknown location is weighted average of the surrounding known values, with the weight decreasing in distance. And the deterministic method, there's no randoms or uncertainty include in the prediction, straightforward and fast. Geostatistical not only put the spatial arrangement but also put statistical property of data. So you will not only consider distance but also consider spatial autocorrelation. That's small variable between the distance, and we have cringing the do assume a degree of spatial correlation between known points and use autocorrelation to distribute unknown values. But so you can just provide certain uncertainty of predictions or variance, and it's more accurate, and they consider spatial variation. Also keep in mind kernel interpolation with battery method also belongs to geostatistical methods. There's no best preference for different methods. Thus, you cannot interpret the context of your study or objectives you have for your model. So you have to create and refine your model based on additional insights gained from the prior knowledge of phenomena or the data exploration to generate more accurate surface. And workflow includes examine data, experiment technique, and parameters, generate surface, evaluate the surface. So first of all, it's examine the data So remember, geostatistical interpolation methods assume your data is spatially autocorrelated. Also remember, stationary means the relationship between 2 points and their values depend on distance between them, but not their exactly XY location. So you must make sure, or you know, the interpreter assume the data is stationary. So if it's not stationary, the transformation to stabilize variance and then use EBK. Unfortunately, geostatistical interpolation requires your data must be normally distributed. So if your data has spatial clustering, it will not properly represent the study area, may heavily influence your model results. Also, geostatistical interpolation requires or assumes that the data does not have any global trends. Also, we need to put into barrier to consideration, for example, cliff rivers and changing soil types. And we have to, in part of examining data, it is necessary to evaluate data steps by firstly visualize the data. And first of all, we have to see like the location, proximate location of the data collected. And the potential impacts of this could be why we have to evaluate the spatial extent of samples because some areas were heavily, potentially will be, heavily sampled than others called preferential sampling. That's a location. And also value, we have to consider value of data points by implementing standard deviation classification. We can see if this data is overall normally distributed. And the ESDA explanatory spatial data analysis is quantitative data exploration by building histogram, which is the
Univariate.
univariate description of your data. We can have a look if this is normally distributed. And the normal QQ plot to compare your data set and standard normal distribution. The axis plots the quantile values of standard normal distribution. You see a zero over here. And the y is corresponding quantile values of the data set. You can see if your point that if it's departing from the normal distribution by selecting them and examine them all of their location on the map. Just notice in this example, uh, ESDA provides us the overall data is not normally distributed, and the lecture recommend we can implement transformation and method called transformation log. Selecting this, you can somehow change the way the data is distributed, and ideally the kurtosis is we prefer in S3 after the transformation it has a minor change. Same as QQ plot and just make some basic transformation. You can make the chart from being this into this. Layer poverty based on the tutorial instruction. I changed the classification method starting. It was natural break. I remember. Yeah, okay, it was natural break. And you know because the data is not really normally distributed, thus we change the standard deviation. The purpose of changing standard deviation that we want to exclude the outliners, and that's why we made this. Characteristic of normal distributed data is mean and median close together. The skewness near 0, the curseness near 3. It's not normally distributed. Importantly, even log transformation improved data, but it's still not normally distributed. The EBK interpolation method has a very flexible transformation that works well for data for almost any distribution, as long as there are no outliers. There are 4 types of output surface. Predict map, just normal thing. Prediction error map. While generating the prediction map, we can have some kind of standard errors. so you can put on the map. These two are kind of interesting. Quantiles, like you can change the threshold of the data. So 0.5 will only result 5% location exist prediction value. So you can, you want over or under predicted value of phenomena, prepare best or worst scenario. And probabilities like this probability that value will exceed or not exceed the specific threshold. So that's called probability map. There's a specific interpolation method called top-to raster that, deliberately interpolate hydrological correct surface from point line polygon data because sometimes there's a bit of water can, do some erosion effect. And so those landscapes has many hilltops or few sinks, and we prefer use topo to raster. The topo to raster interpolation method creates hydrologically correct surfaces. It uses stream input to enforce the surface continuity. Look at this, and prevent artificial dams. So clearly, this is, uh, not deterministic because it put into consideration of the local variation. So that's EBK, one of the best method as mentioned in this chapter. Straightforward, minimal interactive modeling, and primary requirements. It has better results of compared with other methods. Produce prediction surface, prediction standard error surface, probability surface indicating whether critical value is exist, and the quantile surface for predetermined probability level. If you can use local models to capture small scale effects that global crunching model may miss. And here's the basic process divided into subsets, estimate the semi-variogram for each subset. Simulate data at input locations and estimate new semi-variogram, create new final surface. And the median of distribution is shown in the solid red line over here. 25th and 75th percentiles are red dashed lines. And the width of blue lines over there is proportional to semi-variogram weights. So model with smaller weights are thinner lines. You just want to clarify one thing, while I'm reading this chart, it's real. I just realized, why the y value is increasing with the distance increasing because I mean semivariants are the statistical reflections chart of the autocorrelation. So if you have like longer distance between the points, why the y value is increasing? I mean, it should be like decreasing. And by checking the AI, it says like the y-axis value represents the semivariance, and the semivariance is you can see spherical correlation means closer are more similar and further apart. A small distance right here, value are more likely to be similar. Like low semivariance, like that means like the y value represents the similarity. So like low value means like very similar, high value means less similar. And at a certain point, there the curves tend to be flattened out, which indicates beyond that distance, there's no longer any spatial autocorrelation. Thus the semivariance become constant. So semivariance, you can say like you can focus on the variance. Variance means like like the difference between something, right? So like low semivariance, that means like they are very similar. So you can think about it in that way. Also, EBK can check for non-stationary using semi-variograms. And the stationary term is like referring the stationary between the local Okay, so like the graphic depicts the semigram spectrum for two different locations. So while after generating the interpolation surface, you can click different points and compare their semi variogram spectrum. And if you can see, they have a roughly concise spectrum. That means the two locations have the same articulation structure. But if you see that one, so like different points has different spectrum, that means there's the local non-stationary. Like that means uh, by clicking different locations, you can see the stability of the estimates around the individual location and get a sense of whether the whole area follows the same underlying structure. Of course, it's not based on this structure. And the presence of the large difference in spectrum in different locations indicate global non-stationary. So EBK has ability to detect the global non-stationary versus local non-stationary. So for the chart that I just shown to you, it refers to the EBK's ability to detect local non-stationary because you can generate multiple simulations of semi-variogram at each location. Like I said, you can click on the points and allowing to the model capture local variations in spatial relationships. So if they have different statistical properties like different semi-variogram, as I shown to you in small pockets in the dataset, EBK can detect and adjust semi-variogram for the specific area. And local non-stationary, you can analyze if the data set changes across a different across entire region. For example, the mean value of your data set. After you generate the empirical semi-variogram, you can fit a line to the points to form an empirical semi-variogram model. And you have to select a appropriate model to capture the features in the data. And there's a very important sense. The steeper curve near the origin, the more influence the closer neighborhoods will have on the prediction. So you mentioned over here. So further explanation could be a steep semi-variogram near the origin means a close neighbor have a stronger influence on predicted value because vertically drop off quickly as distance decrease. As it is distance increase. And also I mean that's different topic. So there are two charts. One is the exponential model. This one is typically applied when speculation decrease exponentially with the increasing distance, disappearing completely at a different distance. And the second one is K-Basel model applied similarly. It's typically applied when most of the empirical covariance fall inside the confidence intervals and a few fall outside the intervals. So based on the attribute or the property of the chart, you can adapt different model. So we can minimize the deviations from points according to the criteria. And you can open the just the wizarding arc map and so you have to just several parameters prediction of course you won't generate the prediction service type, which is the most common one, and transformation can be empirical, and the semi-variogram type is gonna be K-Basel as mentioned, as K-Basel is the best choice. You're willing to wait longer to get most accurate results, and you can preview the map. So after generating the prediction service model, uh, I don't know how I wrote it back, but it was the monitor station layer has yeah the map outside the boundary. The boundary, I mean the EBK map boundary. So it has some different island sector over here. So like you can adjust mapper property on the EBK surface and click the rectangular extent of the boundary, and you can just eliminate the rest of the area. And second step gonna be change layer poverty data frame, and it was no clip, but you want clip to shape and specify shape. Shape is boundary, which is Japanese map. And click apply. You can have this. And that's the second method of creating picture using the kernel interpolation with barriers. Of course, you know the one can just deal with the barrier like with or without the this K interpolation. You can put barrier into consideration like this. That's the first, like that's the most obvious function. And the second, I want to emphasize the also interpolate uh, and on the local linear trends that be best fit the surrounding points. For example, if you have this kind of point, the kernel one can generate different trend lines in a local, in a local scale, and then generate the lines, that it combines most. And there's a term called, the bandwidth parameter. So you can adjust your bandwidth parameter, which defines distance around location within local method include ability. So if you want the model based on shorter distance between points, preferable in hydrological and meteorological
Meteorologic.
applications. But if you don't supply any bandwidth, the method will calculate user bandwidth and minimize RMS cross evaluation error. So that's a 2 point of the kernel relation with barriers. And the KI with barrier, you have to find this tool in the toolbox right here. And you probably don't want to raster right now because you want to do some, further deep down. Just this is layer and then click OK. Yeah, it's generated. And we do the same. I mean, I already showed you, but and now we're moving to the top of the raster tool. This one's for interpolating topography, and it can create the so yeah, so you can create the for various type of data from contour lines, points, and streams. Can make sure it generate represents the natural terrain accurately, and you can impose the constraints that make sure the drainage structure stream flow naturally downhill, reach are well defined. The screen you can create mimic how water flows across the landscape. And it requires less data, less input data. Also, we can evaluate global drainage condition by feeding the sink. It's just like watershed delineation. So, they are feeding the sink, so you won't, the water course won't get stuck. And that's a very basic workflow. You keep boundary sync, lakes, streams, elevation points, elevation contour, you can generate the surface. Also make sure if you have a sink, the water will just go inside. So that's why your water course will, got trapped at some point. And by the way, I skip this whole exercise because the DEM, sometimes if you can think and make it if you think. The DMA can done anywhere from GE, Google and Google Earth Engine. And Field Think also very easy to do in ArcGIS Pro. So I don't think it's necessary to just build a DEM from this method. But keep in mind, it's just like using the spatial interpolation method to achieve something, and it just achieving something that already be built. And the final outcome look like this. Here's the process of the map. You just put everything and you can generate the rest there. In this section, we can interpreting the interpolation results. We have 3 different maps using the same EBK, but different parameters. and the method to validate our accuracy of the predictions to generate the prediction standard error surface, and the wider it is, the more accurate the interpretation is. And cross-validating is the technique estimates each of the single points based on the model parameters. Uh, then the estimated and compare to actual sample value to calculate the model error. So for example, that's the red dot. And first of all, you based on the rest of the 9 blue dots, you can predict this value, but you have to compare with real value. That's how cross-valuing works. And I mean that's different topic, but they just put together. So you have 4 different masters in that wizard. It can give you some kind of insight of your model, prediction accuracy of the model. First of all, it's called predict graph. Display how well each sample was predicted. The blue line represents the regression equation. The black line is the reference line. The point spread should be close as possible as the gray lines. The better a model, the closer regression equation will align with the reference line. So this line will align. And that's the error displays the, you can understand. Oh, there is standard error and normal QQ plot. If this one's, how closely the error aligns, not the data, okay? So how closely the error aligns the standard normal distribution. And you can make another evaluation by generating the RMS values 3D map. So if that's greater than 1, that means your variability, you're underestimating. If it's lower than 1, that means you're over. I mean, yeah, if you're less than 1, that's overestimating. So this means you're underestimating. So you maybe have to, estimate this even more, like higher value. So remember, we have to consider the optimality and validity. So if you're, each square and then root, so it's called RMS. So the model with small RMS predict error seems optimal because it's accurate based on existing data, but a model has a slightly, but the model has RMS error close to estimated prediction standard error may be more valid because provide more realistic and consistent predictions, especially when predicting error without data. And this is statistical approach of like comparing different models. And the right is EBK, left is KI, and why EBK is better, you have to go through this different categories. So first of all, unbiased, center on the true values. Of course, the EBK is better. It's center on true value. Second, the center mean prediction error near 0. This one, the mean value near 0. So if you check the mean, it looks like KI is better because it's close to 0. But the root mean square standards error is too high compared with the EBK, so that's why even the mean is kind of closer to 0, but we just can't use the KI. That's the first. Also mentioned, the root mean square must close to average standard error to provide the validity. Clearly, the EBK is better because the root mean square and average standard error is closer compared with the KI. Also, it's very important to make sure standard RMS prediction error in your 1. So that's what I said. Close to one, of course, this one. DBK is better. So just in short, you don't have to worry about anything else. Just make sure the root mean square and average standard error if they are close. And that's why root mean square standard closer to one. That's all. You don't have to consider anything else. And you can and you can see the requirement of good quality model has standard mean prediction error near zero. Standard mean standard, okay, whatever. Mean standard, look at this, close to zero. Remember, it is called a mean standard, close to real zero. Mean standard, close to zero. Also, RMS, root mean square, this one, must close to average standard error. And lastly, root mean square standard error, close to one. So basically, if you have a chart like, if you have a table like this, so just evaluate these four different lines. First of all, if this one close to zero, and number four and number one and number four, if they're close together, number three, if they're close to one, that's all you evaluate. I mean, I still cannot remember the name. Okay, I also forgot to mention, you have to make sure you also want this one to be smaller. I mean, the smaller better, but also have to make sure it is small and also it aligns to the fourth one, average and error.